All right, so since I'm extending the due date, I cannot talk about the solution now. What?
So is it extended till Wednesday?
Yes, Wednesday, 12 p.m., right before class. Okay. However, I can talk about a few techniques. Yes.
What if you turned it in? Would that be more important and just didn't go all the way through the steps?
The steps would have been more important.
Yes, the steps are the ones are the parts that will give you points. But obviously, if your steps are incorrect, you don't get all the points, right? Okay, but it is the steps that are actually important. Okay, so a few things that I want to illustrate, just in case we don't get that part. So if you have a negation on the outside, you basically apply De Morgan's law. So this one becomes not A and not B. Is that okay? So I'm using the notation of exclamation point is negation, and then the implicit quote-unquote multiplication is conjunction, and then the explicit addition is disjunction. Is that okay? Because it's just a whole lot easier for me to type like this instead of keep using backslash wedge, backslash b, backslash neg, and so on. Okay, but De Morgan's law also applies to a negation on top of a conjunction, so that one becomes not A or not B. Okay, and then we have distribution. So the basic distribution is just A and then B or C. This one you know already because it is the same as the arithmetic trick of distribution. But the other one also works. So you have A or and then BC. Now I use parentheses. These parentheses are extra. They really usually are not needed because we typically perform multiplication before addition in normal algebra. So in Boolean algebra, we kind of keep that order. We perform conjunction first, and then we perform disjunction if there are no parentheses. So I'm adding these just to be extra clear. This also applies. Now that is actually discussed in the CNF discussion. It is somewhere in there, okay, but it is there, okay. So you can use this. And then we have implication. A implies B is the same thing as not A or B. And then we have association, which means if you have A or B or C, it is really the same thing as just A or B or C. The parentheses dissolves basically when you have a bunch of disjunctions. And the same thing with conjunction. When you have this, it is the same thing as A, B, C because the parentheses do not matter. And then you have the usual commutative law. A plus B is the same thing as B plus A. And then you have the unusual ones, like 1 plus A is 1. Okay. 1 plus A is 1. And then 1 times A is A. 0 times A is 0. Okay, and 1 times A is A. Now, these you can probably get it from the truth table. What?
Do you have two of those?
I have 2 of those?
Zero
Oh.
plus A?
I think 0 plus A, and then we have a 0 plus... Yeah, there you go. There we go. There we go. So we have the identity in conjunction, and then the identity in disjunction. So I cannot imagine beyond these what else we will need.
For some will. For some will.
The fourth one was
The fourth one? Yeah, the fourth one is actually in the discussion, but it is a little bit hidden. So you kind of have to really read it and go like, okay, what did he mean by this? So that's how you get that one. Okay, so let me go over where it really is hidden inside the notes, because you might need to find out how to find stuff in the notes here. I'm using Google Chrome, so I'm hoping it can render the MathJax thing as well as Firefox, because in the past it doesn't do the job. It doesn't do as good of a job. So we go to completeness, use for example, CNF. Okay, I think it's over here. So that one is actually discussed in here. So when you look at this one, it says if you have phi and psi in parentheses or row, then you can apply distribution so that you have phi or row and conjunction psi or row. But I use the English word and here because in the WFF space, we only represent disjunctions. So that's why we basically break this up into two things, this one and this one. And then each one has to be broken down individually. So is that okay? And I think in my own proofs, I have used all of those rules in already. I have applied all of these rules. Oh, there are a few more, but you know those already. P, A, or not A is true. And then we have A and not A being false. So they are good for simplifications and stuff. But I've used those. I've used every single one of these, I think. Pretty hard to avoid. All right. The more rules I give you, the more difficult it gets, because then you go like, I can apply 4 different ones at this point. Which one do I apply? And that becomes difficult. Yep.
I think where I got stuck was by the time I got it after just staring at it, where, for example, A and B, or C and D, and then it hit me that I have to use a distributive.
Right, and then this distributive can be nested.
It's kind of yeah, sort of foiling. And I'm like, okay.
Okay, so you're talking about this one, right? On the whiteboard, you're talking about this one.
Yeah.
Okay, so now the question is, how much can we expand it, right? In other words, what if this is BCD? Okay, so what do you think?
It's just another one with A plus D. Just add another A plus D.
Yep. That's it. Now, if you, yep, go ahead.
I have a question. Because it's associated, can you apply Morgan's law on variables like when you get ands? Does it all
Yes.
get negated with false?
Yes. So you're talking about the negation of A or B or C. Is it the same thing? Okay, this is a question mark because I'm saying, okay, is it the same thing as not A, not B, not C in the conjunction? Okay, so you can probably answer that question yourself because this you can prove using the truth table. So that's why I encourage you guys to try to look into something like this and go like, I wonder whether that works. You can prove it in 2 ways. You can prove it either by Boolean algebra, which is kind of recursion because you're trying to understand Boolean algebra and then you use Boolean algebra to prove it. But you can also use a truth table. Because in this case, using a truth table, you have 8 rows, right? Because 2 to the power of 3 is 8. So you have a truth table. You evaluate this one, and then you have a column. You evaluate this one, you have a column. If those 2 columns are exactly the same, then these 2 expressions are the same. Yep.
Or like also can teach us like logically that when everything is an or, the only time that it's going to be false is over on the bottom.
You're talking about intuitively.
On the top, all of
Okay.
them.
So you're talking about intuitively, does it make sense?
Yeah, like when like looking at it and thinking about the truth table layout.
That can be a little bit dangerous, because intuition sometimes can lead to the wrong path.
This one is just kind of like straightforward and simple. Like when it gets complicated, when there's a mix of ands and ors in the same same function, then yeah, it's that is dangerous. But like when they're all the same, it's a little.
So let's try to do this. Let's try to prove this one using Boolean algebra. Okay. In other words, if I only tell you about these rules, okay, so I give you only the basic De Morgan's laws like this that only applies to 2 variables, and I only give you the associative laws like this one and also this one. Can we prove it, by hand? And the answer is, well, we should be able, right? Okay, tech should be able to do it. Okay? Okay, do you guys buy this? Because I can introduce parentheses within a whole long string of disjunctions anywhere I want, right? So now I can basically look at B or C as one thing, and then we apply the De Morgan's law that only apply to two things. So now we have not A, not B or C. Is that okay? That's one application of De Morgan's law that only applies to two variables involved. Is that okay? Because I'm looking at B and C, B or C, excuse me, I'm looking at B or C as one single thing. So now you have another B or C, and what does that become? Okay, I use extra parentheses, just to be, oops, sorry, wrong key. Just to emphasize that this is the other side. Okay. So when you look at this one, then we can apply De Morgan's law one more time, and then we end up with this. And then we use associative law again to remove the parentheses, because now we have a whole bunch of conjunctions, and then we just end up with the same thing. So you can prove it in either direction. You can either use a truth table, or you can use algebra itself to prove it. Is that okay? More or less? Okay, all right. And the same thing applies to this kind of situation, because the distribution law that I give you can only deal with BC. Okay, so if we only know about this one, then how do we deal with A, B, C, D? It's the same thing. So you basically break it up. So you say A plus, and then B, and then CD becomes its own thing. B, CD becomes its own thing. So now we only have two items in the bigger or the outer conjunction, which we know how to deal with. So now that becomes becomes A or B as one term, and then the other one is A or CD, right? But then A or CD we can apply this again, and then we say that this one expands to A plus C times A plus D. And then at this point we can use associative law and just remove the parentheses, and then we get the same result. But that can also be proven using a truth table. So you can do these things in many ways usually. Are we doing okay so far with all this stuff? Yep.
Or I'm thinking about like the homework. We already turned it in, and we want to give it another shot just to make sure we're going to receive this.
I'm with them on this one, yeah.
Like, you're giving us more time, so I might as well make use of it. But
Okay, but then I have to tell you exactly how much partial credit you're going to get. So I'm going to say 75%. This is all getting recorded.
So turn it in on Wednesday. You get. If I got it like 100% right,
right, it would just be scaled to 75% of the full score on Wednesday.
Yeah.
If you turn it in today, and it's you get whatever you get today. But you have to decide whether to resubmit or not, because if you resubmit on Wednesday, I'm going to grade that one. Okay, I'm not going to grade the one you submit today, and then grade the one on Wednesday, and then let the system to take the maximum. So you have to decide. All right. Okay, so I'm going to give you some more tools to do this homework assignment, because in case you're doubtful, okay, you do a whole bunch of derivation, you go like, I'm not really so sure that I did the right thing. How do I check, right? Okay.
Let's do an example, just a random example.
Huh?
Can you do a different example to show us your step-by-step process?
Well, I'm showing you the individual steps, but you have to put the whole thing together. All right, so to do that, let me see, where's my Google Drive? Let me go find my Google Drive, which is here. Does it use the right account? Yep, okay. So I'm gonna use my Google Drive here, and this one I can put into the share drive, just in case you guys are interested. You can download it and play with it. cisp440 in the share drive. And we'll add a new spreadsheet. Okay. So right away, this one is now already shared. You guys can see it right away. And I'm gonna rename it as truth table. Oh. Okay. So let's just say that I'm not 100% convinced that my algebra is working correctly. So the De Morgan's law that applies to 3 variables, I want to show the truth table to convince myself that that does work. Okay. So the way I usually do this is I have n, we have variable x, y, and z, and let me magnify the display a little bit because otherwise it's a little bit hard to see. So n is nothing more than an integer, okay? So that obviously you guys don't have to do it this way, but I'm just showing you, if I were to do this using a truth table, how would I do it? So I generate, all the rows, like 0 up to 7. And if you think about it, 0 as a 3-bit number is 0, 0, 0. 7 is 1, 1, 1 as a binary number, which corresponds to false, 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 all the way down to true, true, true. So now the only question is how do we assign those true, false values to x, y, and z? In other words, we're doing binary conversion. Okay, we're converting the values to binary and only pick out 1 digit at a time. So there are many ways to do it. The easiest way that I can think of is to do a mod operation that is inside a division. So the division is going to be this number divided by a power of 2. 1 is a power of 2. Okay. Now, for those of you who think, but I want this spreadsheet to be, truly, flexible, I'll give you something that is truly flexible here. Okay, so we put a $ next to the A, which means when I copy this formula to other cells, the reference to the column does not change. It does not, it's not relevant. Okay. And when I divide it, I'm going to use a power of 2. So I would say, this is power 2 raised to the power of, and I know that with column B I want a power of 0, with column C I want a power of 1, and then with column D I want a power of 2. In other words, the column number is part of the equation to determine what the power is. So I need to know what column this particular cell is in. So as it turns out, there is a column function that tells you where the column is. Okay, it's not highlighting, I think. Did I?
C-O-L-U-M-N?
M-C-L-O-L-U. Oh, column. Okay, so when you use just column by itself, it tells you the column number of whatever cell it is in. Okay, and the first column is 1. Okay, so it's not like in C and C++ where it's 0 oriented. This is 1 oriented, if I remember correctly. So you have to do a subtract 2 in this case because the cell itself is B2. So you have to subtract 2 so that the column of 2 becomes 0. That specifies the power. And then you're modding this with 2. Okay. Let's see. The power. Okay, I think I got my parentheses messed up here. I think I got a extra open paren here, so we can just get rid of that one and then close this one. That closes the mod, right? Yep. Okay, let's see whether this works or not. So we just copy a bunch. Okay, alternating, screw it. Alternating. Oh, that is not good because I forgot to take the floor. Okay, so go back to the first one because I'm replicating this one, so I need to take the floor. The floor applies to the division, so we are applying the floor here, and then we are ending the floor here. There we go. Okay. Should not affect the first column, but it should affect the second column. There you go. And then the third column works out too. So I'm giving you this kind of universal tool. You can make the truth table to handle like 5 variables, 6 variables just by stretching it. Okay. Yep.
So if we said applied to homework, we wanted to check our scanner since they're basically the same expression.
They should be the same.
So we make a giant truth table and then plot the not plot, just make the column of the original expression and the one with the CNF and have to be equal first.
They have to be exactly the same. Correct. Yep. Okay. So now I want to look at the original equation. So the original equation in this case is the negation applied to the conjunction of x, y, and z. Okay. And we have a specific column like that. And then the Morgan's law transformed equation is that one? Yeah, it's conjunction in the inside, so now we need disjunction, right? So this one becomes the disjunction or the or applied to the negation of the individual terms. And that one, like so. And then you just make this as long as the other column. And you can see that every single cell agrees. The two columns are identical. So this is, quote unquote, one way to prove that two expressions are equivalent in Boolean algebra. Now, I just chose something that is known to be equivalent. But in your case, you change this one to be the original equation. Now, unfortunately, implication is not one of the operators. So you do not use if. There is such a thing called if. That is not what you want. Okay? If you use the if function, it's going to do something wonky because that's not what you want. Yep.
For when I was doing the homework, I used the online version truth table generator. And it has the implication.
It has implication? Okay. That can be helpful. You can extend Google Sheet using Google Script to also include your own implication function if that is what you want to do. Is that okay? So I'm giving you extra tools and and also a crystallized version of the Boolean algebra rules, which is this part here. And but I can't really talk about the solution now because I'm extending the due date. I can tell you that it didn't take me a whole lot of time. Sean was looking at me going like, because Sean worked it out entirely already, and then he was looking at me how I worked it out and go like, how can it be so short? The key is you want to do simplifications along the way. Okay, that's one thing that is kind of really helpful. So simplifications would include basically these rules. These are all simplifications. And then the other simplification, which can be derived by these rules already, but I'm going to spell it out so that you guys can recognize it. Okay, if you have already turned it in and it is already correct but not necessarily all the way simplified, do not turn it in again. Okay, because all I need in order for it to be entirely correct is that the expression is just correct and it is a CNF. That's the only requirement. Doesn't have to be simplified. All right, so the simplification goes like this. If you have A or B, okay, and then you have A or B or C, this entire thing is just A or B. In other words, A or B or C is simplified out of this entire thing. Okay? Now, I can prove this, once again, using two different ways, or three different ways, okay? One is intuition, but I never prove anything by intuition. That is not going to take computer science very far, okay? I can prove this by truth table, okay? And I already have a truth table, in a spreadsheet. I just have to change one side to read like this, the other side to read like this, make sure that the two columns are the same, and I'm good. But there's a third way, which is to do it by algebra. So to do it by Boolean algebra, we look at these things, okay, like so, and then we do factoring in this case. In other words, we have A or B or 1, and then we have A or B or C. Oops, sorry.
Zero.
Yeah, there's an or 0.
C and not C.
Hmm?
No.
No. I thought I had it once, but now I forgot how to do it. It's part of the reverse of,
Can I do like foil?
huh?
Foil.
It's unfoiling.
Unfoil.
You can do foil. If you foil it, you will end up with a long term,
Yeah, yeah.
and then it boils down back to just A or B. Yes. So you can do that too. Yep. So you can foil it. Hmm? Let me see. But I want to do the unfoil, and I want to do the unfoil trick, which means we have a conjunction of terms already, and I want to turn it back into something simpler. The common part is A or B, so that's my A. Oh, okay, I got it. I got it. Yep. Where is it? It's right here. Okay, so it is A or B or 0 times A or B or C. Okay, and then I group A or B into one single thing. So A or B or 0, A or B or C. So if you look at A or B as one thing, then we can apply the reverse of this step here, because we basically have something or 0 and something, the same something or C. Is that making any sense? So we go in the opposite direction. So now it becomes A or B, oops, A or B, which is just this A on this side, and then we have an extra or, which means this is no longer C and F, but it's okay because we're just trying to make a proof, so it is okay for this not to be a C and F at this point. So we have A or B or, and then we take out the 0, and then take out the C on its side, on the other side. So it becomes the conjunction because we are pulling this out, we're pulling this out onto their own term. Is that okay? Is that okay? Yeah. All right, cool. So now this becomes A or B or 0 because anything and 0 is 0. And then this whole thing becomes just A or B because 0 is the identity of disjunction.
That's what I was missing. I was like missing, like when I was looking at that,
Yeah.
it didn't appear to me of like adding a 0 and just having it simplified to just the first, like whatever the common variables are.
Mm-hmm. Yep.
I'm assuming it also works in a simpler form where it's just A and the thing A or B. So if you just have A kind of times A or B, then that will eliminate the B.
Eliminate the B.
Well, like I'm thinking about it in just simplifying it so that A and B is just represented by one variable.
There's no A and B in.
I mean A or B.
Okay. Okay. Yeah, but that's basically the proof is to look at A or B as one single variable, and then we extract the implicit or 0. We extract that one out along with the or C, but then the 0 and the C will be conjunction together because of the reverse of the application of the distributive law, and then we end up with a 0C, and that's how we got rid of it. Is that okay?
Would you be willing to explain it intuitively after you've proven it to kind of put the pieces together?
Okay, so intuitively it makes sense too, because A or B is, okay, if A or B is true, A or B or C is guaranteed to be true, right?
Yeah.
But if A or B itself is false, then A or B or C may be true. But it doesn't matter because if they're connected by conjunction, if at least one is false, the whole thing is going to be false. So that's why intuitively it makes sense to get rid of a term that is true more often than at least one of the other terms in a conjunction. Yep.
What if in the first part where you have A or B or D, and the second part stays the same, would it still equal? Would it still
Then you
simplify
cannot
the
simplify because then it
It
becomes
would have to
DC
be the
here,
difference.
and it's no longer a CNF either.
Gotcha.
Yeah. So if it is A or B or D, the
Mhm.
whole thing, conjunction with A or B or C, the whole thing, there's nothing you can do that you cannot simplify.
Gotcha.
If you wanted to remain as a CNF, there's no way to simplify any further. All right. And by the way, I never did this derivation before. So today I just like go like, yeah, I should be able to prove it. But that's the whole
Expect that
thing,
to be
you
on
know.
the test now.
Hmm?
Expect that to be on the test now.
No, because you can also prove it using a truth table. So a truth table in this case has 8 rows, and it's not too difficult.
Precious.
Yep.
Sorry to keep asking questions, but I think one time or one of the classes you had like where something handed with itself equals itself. So is that part of the rules?
Yeah, you can use it for simplification. So, I think I forgot to put that here. Okay, more rules. But most of these can be derived from the truth table itself. So, in other words, the symbolic representation of these rules is actually, if anything, adding more to confusion than anything else. The only rules that I think are truly important that you cannot really, these two are important, and then distributions are important too. Obviously, the implication rule is important. The rest, I think, it's just a matter of, understanding the truth table and be able to work with that. Is that okay?
Is there only one answer to this question?
If you want the optimized version, yes. But but since I'm accepting answers that are actually CNF, but they don't have to be simplified, there are many possible answers.
Is the most optimal one, does it by any chance have two parts?
Two disjunctions, yes.
Right.
And then there's only one term of difference between the two disjunctions.
Okay,
Yep.
Hint, hint, wink, wink.
Yep. But to the rest of the class, people who are still working on it, there are many ways to make that happen. So I'm not disclosing the actual answer either.
Makes me feel a little bit better about my You can still get 100% wrong, but maybe
You can still get 100% wrong, yes. Because I can just say it is, it's P or Q or R on one side, and then P or R or T on the other side. That would fit that description, right? But that is not the right
Would you
answer.
get like a -1 if you forget to do a negation, like how in math you like do a negative somewhere else, you get like a -1. You know what I'm saying? It's all wrong.
Well, that's one way to look at cisp440 or any programming class or math class. Is either right or wrong. Makes grading really easy. Oh, if something doesn't compile, don't even bother to grade. Okay, so are we feeling more comfortable? Okay, all right, excellent. So I'm not going to give you the new homework assignment until Wednesday because I need because in order to do the next homework assignment, you need to know the answer to this one first. So that's why I'm not going to give you guys the next homework assignment until Wednesday.
What if you just make it available for us to look at it?
Might got this wrong.
necessarily-
No, because the question itself includes the answer to
Oh.
the current one. Yep.
Is the next assignment involving the resolution?
Yes. So the next homework assignment involves resolution and also proof by contradiction. So that means, it is a good idea to go back to those concepts here and kind of revisit, what those concepts are. So proof by contradiction, are there any questions about proof by contradiction? Because I just want to make sure that you guys are understanding the concept itself. Any questions about proof by contradiction?
So it's like basically like the opposite of the CNF, which is proofs.
No.
Or I mean like we just the
Negate
way we
theorems.
look for the bottom answer instead of them just being the sequences of disjunction, to be sequences of
Nope.
conjunction.
We have to just find out
No,
one.
proof by contradiction itself has nothing to do with resolution nor CNF. Yep.
So proof by contradiction, it basically takes the original formula and proves that the negation of that can be true.
Okay, so it takes this is the essence of proof by contradiction. Psi is representing everything that is either told to you to be true, axioms and stuff like that. So if you make a big huge conjunction of all of those things, that's your psi. Phi on the other hand is a proposed theorem. You're asking, is this true? You don't know. Okay? If phi in fact is true, okay, then you basically, when you combine phi, the negation of phi and psi, that should lead to a false, lead to something that is not possible. Like, x is greater than x itself, or x is less than y, and x is greater than y at the same time, something along that line, something that has to be false. Okay? Now, the proof by contradiction itself has nothing to do with CNF, nor resolution. Okay? It is a very powerful technique to prove something. I illustrated that in the previous class, showing you that if a number is non-prime, then at least one factor has to be less than or equal to the square root of that number. And we are not talking about 1, okay, because 1 is not considered a factor of a number. 1 is not a prime number, by definition. So do you guys remember that example? I mean, that example has nothing to do with CNF nor resolution. It's just making use of proof by contradiction. Well, this would be a good time to talk about the pigeonhole principle, because we can prove the pigeonhole principle itself. Okay, so let me see if I have a pigeonhole principle in one of the modules. I think it is mentioned maybe somewhere, but I'm not sure. Nope, pigeon is not mentioned here.
You had it in one of your previous exams. West.
Yeah, in the previous exam it has one. But I can use it today as an example to illustrate what is proof by contradiction. Okay, so we're talking about pigeonhole principle. Okay. Yep. It is? Okay, thank you. Obviously, I have not read my own notes. Okay, so the pigeonhole principle is really quite simple. Okay, it says that okay, we can look it up. Pigeonhole principle. Okay, one word. Okay, so the pigeonhole principle states that if n items are put into m containers, knowing that n is more than m, so you have more items than there are containers, then at least one container must contain more than one items. Okay? It makes sense to you, right? I got 16 items and I only got 15 cubbies. So and I say, okay, we have to put everything into cubbies. Then at least one cubby is going to have more than one items.
Yeah,
That
if
makes
you stick
sense.
to the rule of everything must go into it.
What?
If you stick to the rule of everything must go into it.
Yeah, everything must go into the cubbies. You're running a daycare, okay? Everything they have to go back to cubbies. So we have 16 toys, but only 15 cubbies. So you know that one cubby must have at least 2 toys, okay? This would be a great thing to teach, to our early childhood education colleagues, so that they can introduce, these things like proof by contradiction at the age of 2 or 3. I think we'll have better voters So in 15, 16 years, you know, we'll get voters who are going to question everything and say, prove it to me. I'm not going to believe that. Okay. So, but how do you prove it? Okay, this is the theorem. The theorem says if n is greater than m, and we need to put everything into the containers, then at least one container is going to have more than one items. That's the theorem. How do you prove it? Now you can say, okay, here, TAC, you know, we have 2 items and 1 cubby. Okay, and the only way we can put 2 items into 1 cubby is that one single cubby to have 2 items. There's no other way. Okay, prove it when n is 3 and m is 2. Okay, then you basically exhaust all the ways of doing that, right? Which is many ways. Because out of the 3 items, how do you choose which one to go into the first cubby, which ones to go into the second cubby? There are many ways to do it. And by the way, we're going to deal with that too later on when we deal with probabilities, discrete probability distribution, and stuff like that. But let's not worry now, okay? Tomorrow's problem, we'll worry about it tomorrow. Okay, so that doesn't seem to work very well, because if you can prove up to n equals to some really huge numbers, I can say, what about if I add 1 to both n and m? Prove again. Okay, I can keep doing that, right? So the way to prove this is to prove by contradiction. What do you mean by proof by contradiction? We keep the premise. The premise is there are n things that we have to put into m cubbies. N is greater than m. We keep that premise. But we negate the theorem. The theorem says at least one cubby has more than one thing, right? So we negate that, which basically means all cubbies have at the most one thing. Okay? If all the cubbies have at the most one thing, then the summation of all the things of all the cubbies is going to be less than or equal to the number of containers. Right? In other words, we know that n is going to be less than or equal to m. But you are given that n is greater than m. So you end up with a conjunction where it says n is less than or equal to m, and n is greater than m at the same time. That conjunction is always false. And that's how you get your 0. So if the negation of the theorem leads to a contradiction, which is always 0, then the theorem itself has to be true. That is how you can prove the pigeonhole principle using proof by contradiction. Is that okay?
So it's because you cannot prove the theorem false, it has to be true.
No, it is quite the other way. You prove that the negation of the theorem cannot be false, has to be false, leads to contradiction, then the theorem itself has to be true. But you get the general idea. That was good. So are we okay with proof by contradiction as a proof technique, but outside of the context of CNF, resolution, and propositional logic? Is that okay? All right. I think there are other proofs in even calculus that you can use proof by contradiction. Is there a median theorem in calculus? If you have a continuous function, and then you take 2 points, you know, let's say one is at y1, the other one is at y2, then one of the midpoints somewhere between these 2 points has to be like halfway between that, right? I think that can also be proven using proof by contradiction. Let's say it does not exist. Yep. Then you can use the definition of what is considered continuous, and that leads to a contradiction. I'm not a math professor, obviously. You can ask your math professor about that proof again.
Yeah, it is mathematics. No, it's called structures.
Discrete structures. It's not discrete structures.
What is?
Is the name of the class discrete structures or discrete mathematics?
Structures.
Discrete structure is the name, but it is also known as discrete math.
Just barely got away with it.
Yeah, barely got away with it.
Well, the math department has never given us any issues of, you know, how come you guys are teaching math? I have never encountered once, you know, teaching here, that a math professor has a problem with that. In fact, I think the reverse can happen. If we say, you know, the computer science is shrinking. The computer science department is shrinking. We don't have enough faculty. Why don't you guys, pick up, discrete math and teach that? I think they're gonna have a fit with that. They're gonna like, no, we're not gonna teach your class, but it's math. It is math stuff. It's all math. It's not programming. No, we're not gonna teach that. Why not? Because it's discrete. We only deal with continuous stuff. You guys deal with the discrete stuff. Well, in some universities, math and computer science are the same department, which kind of makes sense. In some other universities, it's engineering, and computer science being the same department. So.
Some of them, they separate computer science and engineering. Like they have at Davis, they have a computer science department, and they have a computer science engineering department, and they're different degrees.
Correct, but they're both in the College of Engineering.
No. I think science is in letters and science.
Yeah.
Oh.
Computer science is in letters and science and engineering.
In Davis?
Yes.
Yeah.
That's new to me.
Yeah.
Because I went there, and when I was there, computer science was a subdivision of electrical and computer engineering. So computer science was kind of like a subgroup of EE at the time. And then during my time there, they kind of spun off by itself to become its own department, but will still be under the College of Engineering. Not anymore.
I think it was when people might
Politics.
switch.
It's all politics.
Wait, how?
Hmm?
They take pretty much the same classes.
Well, right, but how is it politics?
I think it has to do with funding. It has to do with money.
Block grants?
And money ties into two different things. One, you get money from grants, who writes the proposal of doing research and whatnot. And then two, it has to do with enrollment. So.
And also Chevron. Chevron only gives money to engineering.
And in Berkeley, it's EECS, right? So it is the same department. You cannot just get a double E degree. You cannot just get a computer science. You have to get an EECS.
Yeah.
Sorry?
You can just get a CS degree.
It's BA, it's Bachelor of Arts, it's a Bachelor of Science.
But yeah, exactly. It's not BSc anymore. It's BA. It's Bachelor of Art.
They're both, yeah.
Yep. Can you get a double E degree, like a pure electrical engineering degree without the CS?
You can you can choose a concentration, but you do have to take like lower division CS.
So it is still an EECS degree. Okay. Interesting. All right. Well, okay. So moving on to resolution. Okay. So now we're combining. This is actually something that we talked about already, but I just want to kind of make sure that we understand this. So the overall strategy when CNF resolution improved by contradiction is combined, the way we do it is we first express psi as one CNF. Okay? And then we negate the theorem that you want to prove as another CNF. You can always have one CNF, the conjunction, another CNF. The result is still a CNF. Okay? But that CNF has one special property, because using resolution, which is just a way of implying stuff, okay? Using resolution, at some point we should get to a contradiction. We should be able to get to a zero. If you can get to a zero from the final big CNF, then the theorem that is being proposed is true. Okay, the theorem is a result of psi. If not, if you're stuck and go like, oh, we couldn't get to zero, no matter what resolution we perform, we are getting in the loop. Okay, we're getting back the same terms again and again. Then the theorem is not a theorem. The proposed theorem is not such. It's not a theorem. So the example here illustrated. So this is the illustration of, this is all that you're given to be true, and this is the theorem that we want to prove. So you first have to figure out the CNF that represents the negation of the theorem, which is the negation of phi in this case, is this one. And then you use a larger CNF, which is the combination of everything that you know or is given to be true and the negation of the theorem that you want to prove. And we end up with this one here. And then you try to do resolution. In this case, you cannot resolve to zero. There's no resolution possible as it is. So that means you cannot get to zero. There's no way you can resolve this to zero. So that means the original phi, the theorem, the WFF that we thought was a theorem, is not a theorem. Because the negation of that did not lead to a contradiction. Is that okay? The second example, on the other hand, ends up with phi prime is a slightly different WFF, and the negation of that has this CNF representation. But when you combine that with psi, we eventually resolve to 0, and that means this phi prime indeed is a theorem, because the negation of it leads to a contradiction. So resolution is basically a very, very mechanical way to do implication. It's like, okay, if you tell me this, it implies that is true. If you give me this, it implies that is true, and so on. But until you get to, oh, if you give me this, it implies false is true. Wait, false cannot be true. We have a contradiction. Your proof is done. Is that okay or not? Did we understand all the big pieces and how they connect? Because how they connect is the important part. Good? Okay. All right, so let's see. It's 1 o'clock. We got 20 more minutes. Let's talk about lottery. I could get into predicate calculus, but predicate calculus is an extension of this stuff. So I think we got enough logic for the day. Okay? So we'll talk about lottery. And let me see if I can convince people not to buy lottery tickets today. Okay, so is it Super Lotto, the one that has a huge jackpot? Okay, well, we'll take a look. Super Lotto. No, that's not. Is that a jackpot?
They could have just been recently won.
No, 70 million definitely is not worth playing. Okay, so we'll try to figure out why it's not worth playing. Okay.
When is it?
Huh?
When is it worth it then?
Well, we'll try to figure it out too. But you won't like the answer. For many reasons, you won't like the answer. Okay, so we'll go ahead and talk about how to play. Okay, so let's magnify here. And we want to find the rules. Where are the rules of Super Lotto? Okay, pick 5 lucky numbers from 1 to 47 and 1 mega number from 1 to 27 on the play slip. Okay, so what they did not tell you is the ordering of the first 5 numbers, the so-called lucky numbers, is not important. In other words, it is considered a set. Okay, in other words, you're supposed to pick a set of 5 numbers, and this set has to be a subset of the set of 1, 2, 3, 4, all the way up to 47. Is that okay? Yep.
Can the numbers be repeated?
Cannot repeat. That's why I said it's a set.
Oh, yeah.
Because you cannot have 2 elements being the same in a set. So you have to basically end up with a set of 5 elements, and that set has to be a subset of the set of the numbers 1 to 47. Is that okay? And then on top of that, you can pick an extra number that is from 1 to 27, and this one can repeat a number that we have picked already before. In other words, the second one is kind of like a tuple that is next to the set itself. Okay? So that's basically a lottery ticket. Alright, so the best way to represent it is kind of like this. Okay, so I can pick the 5 lucky numbers, like 31, 1, 16, 23, and 40. Okay? And because I have to combine it with a how do they call it? Super Lotto number. I'm going to combine it with, let's say, 12. Okay, so this can represent a particular ticket, a slip. Okay, the first part is just a set. In other words, if I flip the order between 31 and 1, it's the same ticket. It's the same slip. Consider the same. So the first question is, how many different tickets can we have in total? That would be the first question. Okay. Well, it's a two tuple when the first item is a set. So I'm asking you, how many tuples is possible? Say again? Nope. Okay, let's think about it. The first thing that you choose, okay, so let's not even worry about this, okay? I'm just asking you, if I have 47 numbers, right? How many ways can I choose a set of 5 out of those 47?
47. Yeah, 47 divided by 46.
Okay, so at first glance, it is like, okay, the first thing we have 47 choices, but once you have chosen one, then you only have 46 left for the second one. And once you have chosen 2, you only have 45 left for the third one, and then 44 for the fourth one, and then 43 for the last one. Does that make any sense? But then you have repetitions. Yep, so you can have 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. They're considered different. Okay. So what do we do to get rid of all those quote-unquote duplicates? Okay. So you look at 1, 2, 3, 4, 5, and then you ask yourself, how many ways can I reorder these things? Okay, so answer that question first. How many ways can I reorder 1, 2, 3, 4, 5? I have 5 distinct things here in the bucket, okay? And I'm just worried about, okay, if I need to linearize and see, turn it into a sequence, how many different sequences can I make out of 5 numbers, 1, 2, 3, 4, 5? No. The first one, okay, I have 5 choices for the first one, 4 choices for the second one, 3 choices for the third one, 2 choices for the second last one, and then I only got 1 choice for the last one. Is that okay? So that turns out to be 120, if I remember correctly. Okay. So how do I take this 120 into consideration out of this number? Divided by 120. Very good. Okay. So the number of tickets is somewhat based on this number, okay? Because the numerator is the numerator is thinking ordering is important. Okay? Give me every single way to pick 5 numbers out of 47, and ordering is considered important. That's how you got 47 times 46 all the way down to times 43. The denominator is saying, oh, but you end up with a lot of duplicates. Because the ticket that says 1, 2, 3, 4, 5, it's really the same thing as the ticket 5, 4, 3, 2, 1, which is the same as the ticket of 1, 2, 3, 5, 4, and so on and so forth. And you ask, okay, out of 5 actual numbers, how many ways can we shuffle and represent it? Turns out to be a 120. So when you divide this number by 120, you get the actual number of subsets of 5 elements to choose out of 1 to 47. Is that okay? But don't forget your, how do you call that, mega number, okay? So your mega number is what, from 1 to 27? So you have 27 choices out of that one. So this becomes the total number of possible tickets. Yep. Well, multiplication and division are, you don't need parentheses, but
in sequence, it will have to.
Sure. Yeah. Okay. So there are this many distinct tickets. Okay. So let's figure out what that number turns out to be. Okay. So okay. Thank you. But I'm gonna have to do some calculations with it anyway. So I'm gonna tag it onto this truth table thing. I know it has nothing to do with truth table, but it's just me being lazy here. There we go. That doesn't look like a huge number. It's for, let's see, 41 million something, right? Okay. Sorry? It's only 41 million, exactly. So when do you think it is a good time to buy a Lotto ticket? It depends on your personal belief first, okay? Some people just, for whatever reason, believe that I am more lucky, I'm luckier than everybody else, and there's no reasoning with that person anymore, not with statistics. So I'm not counting those people in. Okay. So if you just go by math, okay, let's say a ticket is $1, okay. So if a ticket is only $1, then you go like, oh, so if the jackpot is $41 million and blah blah blah, then it's worthwhile to buy. Now there are some lesser prices too, but they're not nearly as significant as the jackpot, so we're not going to take those into consideration just yet. Okay, but that's not actually the case because you have to pay taxes. If you buy a single lotto ticket, you win the jackpot. Let's say it is in fact 42 million, okay? And then you say, okay, now I can afford to buy that Ferrari that I have always wanted, and also that Lamborghini, and also that. Okay, so by the end of the year, you spend all the money already. Then comes tax season, and then you end up with just enough spare change to hire an accountant to help you do your taxes, and the accountant will go like, guess what? You go to jail. Because I think at that bracket, the tax is what? How many percent? It's a lot, right? So we're talking about at least 30 or 40%, okay, when you combine federal and state. So out of $40-something million, you have to pay 40% of that as taxes, but you spent all your money already. Okay, so that doesn't work. What if this is like $60 million? Okay, so you have a buffer, you have 33% as a buffer for taxes and stuff like that. Okay, so let's say you ask an accountant, you know exactly how much to break even your taxes into consideration, taking taxes into consideration. Would that be a good time to buy a lotto ticket? No, because they issue multiple tickets of the same numbers and the same combinations. So if the number, let's say this is 100 million, okay, which means you're for sure, if you're the only jackpot winner, you're gonna, even after taxes, you still have a lot of money, okay? You still cannot buy tickets because there'll be a lot of people buying tickets and they issue duplicate tickets. So you can almost count on the chances of having duplicate jackpot winners. They only get like a fraction of the jackpot amount. So I'm pretty sure it is never worth it to buy a lotto ticket. Is that making any sense? But the analysis is kind of important. Sorry?
If you work all this lottery and they split, you're like, well, I guess I'll do it just to make sure some chance in how they win.
Yeah, but then you're going back to the person one, philosophy of, I think there's a chance that I might win, right?
What about 1 out of this much is better than 0 out of that much?
Well, you can also have different other. You can have other reasonings too. It's like, okay, I'm trying not to buy Starbucks coffee, okay, because the additive of Starbucks coffee is just not healthy for me. So you go like, hey, then I got like $4 extra in my pocket today because I'm not buying Starbucks. Okay, well, if you say that it's better spending that money on lotto tickets than buying Starbucks, that's one way to do it, right? But if you look at the math, it is not worth it. Is that okay? Now, other than this, they also have, so there's only one person that can win this prize. So the chances of winning the jackpot is 1 in 41 million. Is that okay? What about the other prizes? Because if you check out their website, there are other ways to win the Super Lotto too. So when you advance play, buy, dream. What is your $1 million dream? Not to pay taxes, maybe. I mean, a millionaire is not really that wealthy anymore. If you think about, the severance packages of CEOs in some really large and well-known companies, they're in hundreds of millions already. So $1 million is not that much money, at least not to those people. But there are different ways to win. Mm-hmm.
It is if you invest it though.
Okay. Oh, they got all the numbers. So this one is all 5 of 5. In other words, your Super Lotto number is not matching. That's what it is. Okay. So if your jackpot number, if that number is not matching, we 5 more minutes. Yes. Yep. We got 5 more. Okay. So we are looking at basically this number, but this time we do not multiply by 27 anymore. In other words, the chances, or the other way. Okay. Let me look at it the other way. Ah, come on. Okay. But there are 26 tickets like that, right? Because these 26 tickets will match all the lucky numbers, but not the super lotto number, right? But since only one is matching all the numbers, there are 26 of these, so your chances. Okay, so if you look at the chance, which is this number divided by the same number over here, that's your actual chance of winning the jackpot. But do you see this number on the website? No. What number do you see instead? You see odds 1 in something, but when you look at this number, most people who do not understand reciprocals will look at this number and go like, yeah, whatever. But if you give them a number that has a point and then a whole bunch of zeros and then some actual numbers, then go like, that seems pretty small. In other words, this can be deceptive. Okay, so when you look at this number, let's check our math and see if it is right. So we go back to our spreadsheet. Okay, so this is basically the 1 in chance. Okay, so the 1 in chance is basically this number divided by this number, and we should get. No, it's the correct one. So are we getting the same chances? Yep, 1 in 1,500,000 something. Okay, so we got that back. Okay, this one is any 4 of the 5 lucky numbers and the mega number. All right, so how do we work that out? So we take this number, it is the same, out of the same number of numbers, but now the question is how many tickets will match 4 out of the 5 lucky numbers and also the mega number. That's the question. Let's forget about the mega number first. Okay, how many tickets? How many ways can I match 4 out of the 5 lucky numbers?
It's 47.
Like 47 and 46 times 24.
Nope. It is actually a little bit easier. Okay, because by the time we do this, we get to do this calculation. You already have the lucky numbers picked out, right? So you have 5 lucky numbers out of the 47 numbers, and then you have the other 42 not so lucky numbers, right? So now the question is, how many ways can I choose 4 out of the 5 numbers that are known to be lucky already, and how many ways can I choose 1 of the not so lucky numbers? That becomes the question. So now the question is, how do we choose 4 out of the 5 lucky numbers? Now, without showing you the definitions of these things, the first one is a combination. 5 choose 4, okay? And then the second one is also a combination, but this time it is 42 choose 1. Okay, so let's look at this. I'll explain what a combination is later, okay? But it's also called choose. 5 choose 4, 42 choose 1. We got 5 lucky numbers, 42 not so lucky numbers. Out of the 5 lucky numbers, we want to choose 4. Out of the not so lucky numbers, we want to choose 1. And you have to do the multiplication, because for each way of choosing 4 out of 5 lucky numbers, there are 41 choose 1 ways to choose a not so lucky number. That's why it is a multiplication. Is that okay? And then we have to remember there's a times 1, because out of the 27 numbers that you can choose as your mega number, only 1 matches the actual mega number. The other ones are non-mega numbers, so to speak. Okay, so we end up with 210 of these tickets. So when you look at the chances, it is approximately 197,000, and we will check the website. 197,000. It does match. Okay. Okay, so the next one down is going to be, okay, this is going to be the same number, and then but this one's going to change. So we'll copy and paste, but the only thing we're going to change is the 1, because we still have 4 out of 5 lucky numbers and 1 out of 42 unlucky numbers, or not so lucky numbers. But this time we are looking for a number that does not match the mega number. There are 27 to choose from, and you have to pick the one. You have to pick one of the non-mega numbers. So there are 26 of those. Okay, and the chances of winning that particular prize gets down to, there are 7,500 or 7,600-ish unique tickets that can win that. So you have 7,000 or so, and so the chances of winning is improving because it's 1 in 7,500. Is that okay? And then they have lesser prizes too, like matching 3 out of the 5 lucky numbers, and I think they work all the way down to 2 out of the 5, or maybe even 1 out of 5 lucky numbers. So again, really, you can get really small prizes. But these smaller prizes, in terms of money amount, is not that much. So it's not enough to really offset, how much. It's not enough to offset when is it a good time to play Lotto. But it is the smaller prizes, which occur a lot more frequently, that keep people to go back and say, "Oh, I'm kind of lucky today because I got the lowest prize. Next time I'm gonna get something better." Because if they only have a jackpot, nobody's going to play. But if they have all of these smaller prizes and it's a continuum of these things, then people they can get people.
It's like the equivalent in a casino where on the slots where like you almost landed.
Yes, the slot machine is a good example because sometimes they just give you something, right? They have done experiments on animals where they have a button. If the button always releases food, then the animal would just learn it and go like, I'm kind of hungry. You hungry? Okay, let's go. Get some food, munch, and then they just walk away because they know, whenever they need it, it's there. But when they don't need it, they just forget about the whole thing. And then in the opposite spectrum, you can say push the button, and it doesn't give you anything. Animal learns it and go like, doesn't do a single thing. It's only when you have a button that probabilistically will give you something, then the animal just keep hitting it like crazy. They have done experiments of these things on monkeys, rats, and other animals.
The pigeon ones.
Is it the pigeon ones?
Yeah, usually it pegs up.
So how many buttons and how many pigeons? Can we get back to the pigeonhole principle? Or 2 pigeons pecking on the same button?
Oh yeah, it had to do like a turnaround, then press the button.
Oh, okay.
So it learned that whole.
Yeah, but behavior cannot be explained once things are probabilistic because animals just go crazy when they to push those buttons. Yep.
But then again, animals don't have the cost to pressing that button besides just pressing the button. Like when you're
I think even when I can be wrong, but I think even if you associate like opportunity, probabilistically speaking, that you can get the electric shock, animals will still do it.
Oh, really?
When there's a chance of reward, they will still do it. It's strange.
Well, at that point,
Yep.
it's like every time they fail, they get like shocked or zapped.
Well, it's probabilistic. Sometimes you get food, other times you get nothing, other times you get punished, and they will still push it. All right, we'll continue this on Wednesday. No, I forgot.